All right. Number 1. Chapter 6, test observations. Number 1, be able to ID the type of differential equation. Because I can't blame anybody for starting off with separable. No, that's the nice one. It can still be long, that's nice. Okay. But if you cannot, you must be able to separate to do separable. You got to put all the y's and dy's on one side and all the x's and dx's on the other side. If you can't take all the y's and put them on one side and all the x's on the other side, or whatever the other variable is, if it's t or whatever, it ain't separable. That's a hint. That means it must be homogeneous or first order linear. Okay. That's very, very important. Very, very important. Okay, 2. Must be able to separate variables in order for the diff Q to be separable. The other one is we had homogeneous and first order linear. Now, if you couldn't separate them, the next thing to have tried was, is it homogeneous? Can you write it in the form m of xy dx plus n of xy dy equals 0, where m and n are homogeneous functions of the same degree. You got to show that. I don't think anyone even attempted this, but you got to show that. Must show. And then you let y equals vx and it becomes separable. If so. And then you'll y prime is v dx dv, right? So that's the homogeneous. Now, if it's not homogeneous and it's not separable, the only other one we did was first order linear. That's where you let u of x is e to the integral p of x dx, but you got to integrate to do that. The other thing is, once you separate, you got to be able to integrate both sides. Once something is separated, you've got to be able to properly integrate both sides. And this is where the derivatives came back to haunt. If you don't know how to take derivatives, you're not going to be able to integrate. The mistake I saw most was trying to let everything integrate to a logarithm. It's not necessarily true. Everything doesn't integrate to a logarithm. When does something integrate to a logarithm? When you have a function on the bottom and its derivative on top. Right? So for example, integral let's see here. The integral of something like that does not equal the log. For one thing, the top isn't the derivative of the bottom. But everything was integrating to logs on papers, and I didn't keep track of whose paper I was looking at. Right. What would you do in this case? You would let this be u, right? Then du is what? So you put a 2 there, 1/2 there, and that would give you du. Okay. And so this would be 1/2 integral u to the minus 2 du. And I'm not doing one exactly like it's on the test, but I'm doing one that's close. So how do you integrate that? You add 1 to the exponent, divide by the new exponent. It's not a log. So you add 1 to the exponent, divide by the new exponent. Right? And that is something like that. Now instead of 2, how about if you had a 1/2? Same thing. How about if you had cubed? Same thing. You got something to a power, which is the -2 power in this case, times something that can be made into its derivative. The derivative of the inside, not the derivative of the whole bottom. Let me say that again. Up in the top, you have something that can be made to the derivative of the inside. This is the chain rule in reverse. So if someone doesn't know how to apply the chain rule, which is the derivative, you're not going to know how to apply it in reverse. Integration by substitution, which is section 4.5. Integration by substitution is nothing but the chain rule in reverse order.
Only 1/2 comes from the square root.
This 1/2 here?
Yes.
No, it comes from the fact that you needed to make the derivative here up there. So it comes from that 2. Right? It comes from that 2. So you have to have a function to a power and then the derivative of the inside on the outside somewhere. Okay. Just the same way when you do a derivative like d dx, what's that going to be? That's going to be, you bring the 3 down. You take this to 1 less power. And then the derivative of this goes on the outside. And the derivative of that is 2x plus 1. So when you differentiate, the derivative of the inside pops out.
It's 3x squared.
Oh, what am I doing? Thank you. Yeah, what am I doing? The derivative of the inside comes out. And so when you integrate, you've got to have the derivative of the inside floating on the outside somewhere to go back in. So here we have a function to a power, to the -2 power, and then the top can become the derivative of the inside if I put a 2 there. So I put a 2 there, divide by 2, effectively multiplying by 1. And so this becomes set up as u to some power, the inside to some power, -2, times its derivative. Now, I personally don't do the UDUs when I do something like this. If I see something to a power, I look for its derivative, try to make its derivative on the outside, compensate, and go. Right? Right? Now, by the way, I didn't actually finish this one. I should probably do that. Number 3. I didn't actually finish that. You shouldn't leave your answer that way, right? Because you got to substitute back. That's going to be -1 over 2u. 2, what is u? That is really the final answer. You got to get rid of the u's. And if you took the derivative of that, you would get that. If you took the derivative of this, you would get that. So I cannot impress upon you enough. You've got to get the derivatives ice cold. Now, chapter 7 is kind of a reprieve, meaning that it's not, chapter 7 is not dependent on chapter 6 as much. But it will involve integrals. Because chapter 7, the topic is applications of integrals. So you're going to have to know how to integrate, number 1. Number 2, and this is the bigger one, chapter 8 is nothing but integrals. One integration technique after the other, after the other, after the other, after the other, right? It is the brick of Calc 2, is chapter 8. But it's the most powerful chapter. You learn the most in chapter 8, in my opinion. It's a lot harder to integrate usually than differentiate. Right? It's a lot harder. And you're going to, all the integration techniques that we've talked about up till now, you cannot be learning those. Even in chapter 6, they brought bad consequences if you didn't know. Which is why, what was the first thing I did? First day of class, I announced 2 quizzes. I know I went down on your favorite professor list then, right? Who else announced, I'm supposed to kill the whole first day of class with the syllabus, right? First day of class, 2 quizzes. The reason why? I want people to bone up on their derivatives. Absolutely. Absolutely. And by the way, in Calc 1, first day of class, I announced a quiz on trigonometry, remember? Oh, yeah. Right. Why? Because even in Calc 1, but in Calc 2, here, we're going to be doing trig like you wouldn't believe in chapter 8. You are going to go cuckoo for Cocoa Puffs at how much trig is in chapter 8. All right. So if you're weak in trig, on one of the quizzes, there was that derivative of cosecant. Derivative of cosecant is cosecant cotangent, right? Now, if it's cosecant of stuff, if I have cosecant d dx, cosecant of, say, u of x, some function of x, right? That's going to be minus cosecant u of x, cotangent u of x, right? All times u prime of x. And that's what's on that sheet. I handed out the solutions, right? I handed out the solutions. Right. So what would I recommend you do with these? I'd recommend you go over every molecule of toner on that paper, on the solution paper. Every single molecule. And if you don't understand it, do something about it. Do something about it. The derivatives I chose on there were medium. Now I agree, especially on quiz 2, that top derivative was a lot harder than the bottom. Those worth more points too. Okay, but that top derivative is where you really needed to know the chain rule. You really need to know the chain rule. And it had a sloppy looking answer, but that's calculus, right? That's calculus. the last thing I would impress upon you is learn Miller maneuver, right? You needed that for those derivatives. Learn the Miller maneuver. Now, all this we say, we haven't even gone into the tests. We just talked about common mistakes. But this is the bulk of it. So, for example, on number 1, you had to be able to recognize what type of differential equation it was. And then if you thought it was separable or whatever, or something that could be broken down into separable, you got to separate. You got to get all the one variable on one side and all the other variable on the other side, and then you got to know how to integrate those two. And none of the integrals were hard. There were no sloppy integrals. They were the basic integrals. So if somebody doesn't say separate correctly and then tries to integrate, and then they integrate incorrectly, you're kind of wrong from top to bottom. Right? You're kind of wrong from top to bottom. If a differential equation is homogeneous, and you try to do it by separation of variables, you won't be able to. You won't be able to separate those variables. Right? If it's first order linear, you try to do it by separation. You're not going to be able to separate the variables. You're not going to be able to get all the x's on one side and all the t's or y's on the other. You're not going to be able to do that. And then if you go ahead and try to like for example, you integrate something with respect to x, it's got x's and y's still in it, you're off in la la land. I mean, you're irrecuperably. I mean, it's like driving to I-80 and you want to go to California and you turn left. Right? The only way to get there is to go to California is to go 24,000 miles around the world or something. You know what I'm saying? You're not going to get to California. You're going to be lost in the outback of Iowa or something. Okay? Don't do that. You got to be able to recognize the homogeneous. And I don't blame anybody for first trying to do it separable. But if it doesn't work, if you can't separate the variables, you got to do one of the others. All right. And just to let you know, on my paper, that was how much work I had for number 2. It was a fair amount of work, but it was just like we did in class. We did these in class, did several, right? Number 3, not quite as much work actually. This was my work, okay? 1 or 2 of these might have actually been able to do it a different way, but they were all 3 set up for a particular differentiate or a particular method of solving a differential equation. Number 4, mixture problem, right? Mixture problem. We did, right? It may not look like it, but what is here is very similar to what we did in class. It's even similar to the problem we did in class. And I gave you a hint on how to set it up. So if you'd gone through what we did in class and problems in the book, right? So Jesus, you asked me, there's going to be a word problem on the exam. You said one like that. I didn't want to say it, but it is. It was a mixture problem. How swell am I? I'm a swell guy. It was a mixture problem. Again, I'm not going to lie to you. It was some work. That's how much work I had to do. However, I think I have it done twice on here. I have it done once. I actually, in my answer key, I have it done once with one method, and I have it done once with another method. So 2 of our methods that we studied, 2 of the 3 work on this, on solving. But you got to get the right differential equation. And I told you how to do it. I said, let your dependent variable be the amount of pollutant, and then set up dy dt as the difference of incoming and outgoing pollutant. Okay. And by doing that, you'll get a differential equation that can be solved using the techniques we did. Number 5, I told you it would be one. This is the one I told you. Look over every part of it. It was long. That's how long it took me to do it, right? Longish. But look over every single part of that one problem. But it wasn't just that one problem. We did this in class 3 or 4 times. We did it for Newton's law of cooling. We did it for exponential. We did it for the logistic function. Okay, we did it several different ways, or not different times, the same thing, where you describe how population changes and you put that into the form of a differential equation. And so here you're told that the rate of change of the number of coyotes in a population is directly proportional to that expression. Directly proportional to. 2 things are directly proportional if y equals k times the other one. We did that in class. And so take a hint. Take a hint. You know. I don't know how to say this. I could say this in the wrong way and get fired, you know? It's like, do it. Have you ever told one of your friends, well, I don't know if she likes me or not. Can you take a hint? Right? Open your eyes, dude. Okay, right? When I say something like that, when I say you gotta, I ain't lying. Would I lie to you? I'm not lying. Learn how to do it. All right, and that was it. So I'm the first one to tell you that I told you the very first day of class. You start off in this class with a subject that keeps people off balance a little bit. The differential equations is nothing like Calc 1. That I'll hand to you. But I tried to be clear, very clear on what to expect. I tried to be fair. All right. Anyway, okay, let me get those back from you. You will have until Friday to come by my office, and you can come by and look at it. But you have until Friday to come by and make corrections. All right? Make corrections. So work around your baseball practice. All right? Make sure you're not crammed. Make sure you have enough time. If you'd like to do this back over there, I can send this back across campus. If you'd like to do it, just let me know either way. Okay? All righty. Okay. The good news is, like I said, we have a sort of a fresh start here. Chapter 7 doesn't depend very much on chapter 6. Yay! Right? Bad news is twofold. The things that made chapter 6 difficult will make chapter 7 difficult, and chapter 8 absolutely impossible. Not difficult, absolutely impossible. There's no can do it. You can't do it. And I've told you my story. I learned that the hard way, and I don't want you to. The good part is, I had Calc 1 and Calc 2 in an auditorium. I didn't even know where the dude's office was. And in most days, I got the impression that guy would probably do better off not seeing me anyway, right? They didn't even want people to go to their offices, right? And when I got to be a graduate student, I used to get my office mates ticked off, and you had 7 office mates. I had eight graduate students in one office. One office, 8 graduate students. And it was an office about maybe from this wall to the end of to the back. I don't think that long. And then maybe from here to that wall, 8 of us in there, 8 desks, right? And we were packed, chalkboards everywhere, right? That's the way math people roll. And I used to push my office hours. And they go, oh no, I'm getting out of here. Miller's office hours are coming. I'd have students come in, they were sitting on their desks. They were sitting on top of file cabinets in that office. Right? I really wanted to welcome people to come in and get help. And I hope I'll made you feel that way. Moving on. Let's see here, where are we at? We were down here quite a ways actually. We were doing disk. We've done that. Is that it? Right there. Okay, we're about to do the washer method. All right. Get over here. The idea of a washer. We're going to work our way up to it. Okay. Find the volume of the solid formed by rotating y equals x squared about the x-axis, bounded by x equals 0 and x equals 1. Now you remember, I said the disk method and washer method by extension. Washer method is where you're subtracting out a portion in the middle. Okay, like a washer. It's got metal around the outside and a hole in the middle. You do the disk method, washer method, when it involves a function of a variable, say x, revolved around that variable's axis. In other words, the x-axis. So here we have y equals f of x revolved around the x-axis. When it's revolved around the same axis as the dependent variable, you can use the disk method. When it isn't that way, you have two choices. One is to use the method we're about to do, the next part, called the shell method. Or two, you have a function y equals f of x and revolved around the y-axis. You could solve for x and make x equal f of y, and make it, if it's a revolved, make it a revolved thing around the y-axis. That way you have something around the revolved around the y-axis in a variable of y instead of x. We're going to do one of those. But what do you have here? Y equals x squared. Y equals x squared. Revolved around the x-axis from 0 to 1. So from 0 to 1, we have this section here, 0 to 1. And so that section is revolved around the x-axis, and it creates a little trumpet. Oh, we got a good trumpet problem coming up here in this section, in this chapter. Gabriel's horn, one of the great paradoxes of math. I'm serious. All right, and so our question asks us to find the volume inside. Right? Well, volume is what? Pi integral a to b of whatever the radius function is squared dx. And so here, this is our radius function. That is our x. And so that is going to be pi integral from 0 to 1. 0 to 1. Our radius function is x squared, which itself gets squared, dx. This is pi integral 0 to 1 x to the 4th dx which is pi times x to the 5th divided by 5. I'm going to put the 5 on the outside, from 0 to 1. You plug the 1 in, you get 1. Plug in 0, you get 0. So that's just pi over 5. Fairly straightforward. That is not even a Washer method problem. In fact, the next two aren't. I got to come up with a good Washer problem here, right? But any questions on that? Now, well, here. Well, I'm going to make sure we get to a Washer problem, especially after the Washer slides. Find the volume of the solid form by rotating that about the y-axis. Remember what I just told you? The disk method is for functions of, say, x revolved around the x-axis, or for function of y revolved around the y-axis. Here we have a function of x revolved around the y-axis. It's not the same axis. So we have two choices. One, wait for the next section. Or two, use this. We're going to recycle. Except now we aren't revolved around the x-axis. We're revolved around the y-axis. Right? Okay. But now we have a little bit of a problem in that our function is of x revolved around the y-axis. That is not the setup you want for the disk method. So we're going to, our solution is either wait and do the shell method, which is coming up here, or solve for x. And this curve can be seen, and now notice only the bold part of the curve is rotated, not both sides, just that bold part. That's all you need to generate that bowl, right? So this curve here is x. Oh, you know what? Why do 1/2? You got to take the square root of 1. So x equal square root of 1. So we're viewing this as a function of y revolved around the y-axis. So I'm going to say solving for x for gives us a solid generated by revolving a function of y about the y-axis. So you have a function of y about that axis. Ergo, can use disk method. Right? So now our volume is going to be, what I'm going to do, our volume is going to be pi integral, and it's going to be a dy. dy. And what do we put in here? We put in what our function is. Here, it is y to the 1/2 squared. And what does y go from? In that solid, y is going from 0 up to 1. So it's kind of a coincidence that this stays 0 to 1. That's sort of a coincidence. That doesn't happen usually. So that is pi integral 0 to 1y dy. What's the antiderivative of y? Y squared over 2, right? So that's going to be pi over 2 y squared from 0 to 1. And with the fundamental theorem of calculus, you plug in the 1, get a 1. Minus, you plug in the 0, you get a 0. So this integrates to 1 minus 0 pi over 2. I'm going to add one more step here. Add one more step there. Applying the fundamental theorem of calculus with pi over 2. The point of this problem is that we had a function of one variable revolved around the other variable's axis. Not that way, at least, set up for this method. In order to use the disk method, we had to get a function of one variable around that same variable's axis. So since you're revolving about the y-axis, we had to write our function as a function of y. Okay. You are going to see this problem probably 10 times between now and the end of Calc 3. And my purpose is not going to be because you don't know the solution to the problem, is that it is a very good, how should I say, introductory problem to so many different techniques. So we're going to be doing this a bunch of different ways, all through Calc 2, all through Calc 3. Now, the volume of a sphere of radius A. We have to represent that volume as a rotated solid. A rotated solid. So, let's go over here. A sphere of radius A. There's my sphere. It's a nice sphere. Don't you think so? I think so. All right. And the radius is A. So the radius starts there, goes out to the surface, and that distance is A. And so we have here the x-axis, y-axis. How can I represent that as a rotated solid? Well, it certainly looks like you could rotate something, right? For example, I could rotate that function there about the x-axis. Right? If I rotated that around the x-axis, I would have like that, right? That's the function. Rotated around the x-axis. I don't like the way that came out. Down here. Question, what is that function? What is that function? What is the equation of a circle? Please tell me you know the equation of a circle. X squared plus y squared equals a squared is the equation of a circle, of radius a, right? This is a circle of radius. That's the whole circle, which, by the way, is not a function, right? It's not a function. So I wind up with solve for y here. Now I have a plus and a minus, because naturally this circle, don't write this on your paper, but this circle would go all the way around, right? It would go around this way too, the whole thing. But we don't have to rotate both sides around the x-axis, just the top or the bottom. I'm choosing the top. So the top is going to be the positive one of these two. So this is going to be square root a squared minus x squared. So sometimes it's not the disk method itself that takes your time. It's figuring out what function it is, how to represent it, how to get it in shape for to apply the disk method. I don't know if you've ever painted. You ever painted like a room? Right? What takes the most time in painting a room? Is it the bucket, the paint, and going like this? It's getting the room ready to be painted, getting all the junk out of the room, taping all the light switches, patching that hole in the drywall that your little brother put, right? Right. I'm just keeping it real, folks, right? Keeping it real, right? It's doing all that. Oh yeah, putting down plastic. You don't want to ruin mom's carpet, right? You know, ruin mom's carpet. That's going to cost a limb, right? Okay, you get the idea. Oh, taking down curtain rods. Oh, all the mirrors and paintings and pictures. Oh yeah, you got to fill in all the holes from the nails that you put in for all the stuff you hung that you don't have hanging anymore. You got to scrape off the sticky tack that didn't come off for your favorite poster, right? That's what takes the time, and this is the same way. The technique itself, you need to know how to do. It takes practice, but it took a little time to figure out what's getting rotated, and it's this top thing that's getting rotated. Not only that, what are we?
Easy bottom rolling, scum sucker.
Just got to get that for the record. Maybe I didn't get that. Did I? Oh, good. We did. Oh, yeah. I'd hate not to have done. This generated will do an entire circle, right? So if here, watch this. So my volume, pi integral. Now remember, what are our bounds of integration here? Think about that for a second. What are our bounds of integration? But we'll do that in a second. What goes in here? It's going to be something squared dx. What goes in there?
Square root.
Ah, there you go, this thing. Exactly. So that's going to be square root, right? Now, what are our bounds of integration? To get the bounds of integration, I need to go back to my drawing here. Your drawing is very important. So, guess what? It's that special time. Let's see if it will. See if it's going to It's crashing. If it won't let me scroll, that's crashing. Let's see if it. See how much we salvaged. Oh, good. What are our bounds? Our bounds are the bounds on this. What values of x are represented in the segment that gets rotated? Right? So, what is this point and what is that point? I'll give you a hint. It's not 1. It's not 1 and minus 1. What's the radius of our circle? One, 2, 3, 4, 5, 6. A. Good. A. 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 So this is A. Over here is A. Over here is minus A. Those are our bounds of integration. Now, the student will observe we have symmetry here. We have symmetry. Either one of these, either half, will generate half of the volume of the sphere, right? So this is going to be easier if I do this. Oops. What do I get when I square that? A squared minus x squared. How about going from 0 to 1? Did I say 1? Oh, I did not say 1. A. And put a 2 out here. So it's as if I'm revolving just the right half of that circle. And zeros are easier to plug in usually, right? Now, you don't have to do that. That's optional. But bottom dwellers, we like it. And that's me, right? So
Where's that 2 in front again?
because I went from 0 to A instead of minus 8A.
Oh, okay,
So
okay.
I'm revolving only that segment instead of both halves. And zeros are easier to plug in. That's why. I would encourage you to always use that kind of symmetry. That's my opinion. You don't have to. So 2 pi. Integrating now with respect to x. X. A squared is a squared x. The antiderivative of minus x squared is minus x cubed over 3 from 0 to A. Now, when you have a 0 on the bottom, don't get used to writing 0 when you plug it in. A lot of times it is 0. In fact, it's 0 so often, we tend to think when you plug in 0, you get 0. This is going to be 2 pi brackets. Plug in A, I get A cubed minus A cubed over 3. Oh, you know what? What I said was true, but it doesn't happen. If you plug in 0, I do, in fact. You're plugging in 0 for x. You do get 0 minus 0. Don't get used to just writing 0 every time you plug in a bottom integration bound of 0. So this is 2 pi times A cubed minus A over 3 is what? That's the same as A times 1A cubed minus 1/3. 1 minus 1/3 is 2/3. So that is 2A cubed over 3. And that equals 4 pi A cubed over 3. And that is the volume of a sphere of radius A. And like I said, we're going to be doing that many other different ways. So what's the takeaway from this problem? Number one, you got to know the basic equations of circles and stuff, right? By the way, a couple days ago, we did, remember the cone? Remember the cone problem we did? Here's my clicker. Right here? Yeah. Be able to do something like this. Be able to do something like this, where you had to represent the cone as a portion of a line revolved. And you had to figure out what the line was. Well, the line has a certain slope, and that slope was the rise of r divided by the run of h. You're told that the radius of the cone is r and the height of the cone is h. And so we aligned that along the x-axis. Is there more than one way of doing this? Absolutely. You know, maybe Cassidy gets in a cranky mood. She does all the time. She's just so that way. Maybe she wants to put the opening of the cone there, and she wants to do it this way. Perfectly okay. Go ahead and be cranky. That's perfectly okay. Right? But you have a different line. It would be a negatively sloping line of the be negative r over h, right? And the problem would work a little. And we get the same answer. You get the same answer. So there's more than one way to do these. Okay? My point is, you got to be able to do them at least one way. So you have to be able to set that up. And what throws people here is you have height r, radius, height h, radius r. I didn't say height 5, radius 2. That would be easier for most people. Here you're doing the general case, h and r. Down here, the general case, sphere of radius a. Sphere of radius a. So it's the setup. It's getting yourself ready to apply the disk method that took the time here. So you had to boil down. You had to figure out what function it was. You had to know that the radius of the equation of a circle, which is a 10th grade geometry problem. Okay. There's one for next. Oh, we don't want the answer. What happened there? Oh no. Let's see if we can dig up the answer somewhere. Let's see if we have anything from last week. So right here. There. Oh, look at that. We got the same answer 2 years ago. That's always nice. That doesn't have it either. Uh-oh. That is slide number 21. All right. Go back another year. Or I could just work the problem. I'm too lazy. Uh-oh. There. That's not the same problem. You know what? Maybe I don't have an answer. I'll get that to you, okay? I'll get that to you. And that is there is a nice washer problem that we'll do for next time, okay? All right, so we'll keep it there. Come by tonight, you want help? Or just an hour to study. You don't have to even, get any calc help, but you go by, at least it's an hour of quiet study someplace. They usually put me on the first floor. You walk in, go as straight as you can after you walk in the building. Just go straight as you can. You have to do a little zigzag, but not much. Right across from the coffee pot. They know that. You got to be near the coffee pot. See ya.
What is it?
You too, sir.
Thank you.